In this video, we are going to discuss about L1 vs L2 regularization. So basically, L1 regularization adds the absolute value of weights to the loss function. It basically encourages the sparsity. Many weights become exactly zero, whereas L2 regularization adds the squared value of weights. So this doesn't force weights to zero, but keeps them small. Both are added to the loss function during training phase. So basically, regularization helps control overfitting by penalizing large weights that could make the model overly. So let's start implementing the code. First, we have to import the required libraries and gonna import the MNIST dataset for training as well as testing purposes. So first, we're gonna do training and testing on three models. The first model is model none, therefore with no regularization. Model L1 uses the regularizers of L1, and model L2 similarly uses the regularizers of the L2. So this is the training phase. We have trained for 20 epochs. So this is the validation versus validation accuracy comparison across different models. So we can see that all models improve rapidly for the few epochs. The L1 model starts off slower, but due to the strong penalty, it keeps on increasing. Basically, it starts slow because of the stronger penalty, whereas the L2 model shows a smoother curve and slight better generalization. The non-regularized model sometimes peaks early and then degrades, indicating it's kind of classic overfitting. And then here we can see the validation loss curves that the L2 regularized model generally achieves the lowest loss, whereas the L1 has slightly higher loss due to its sparsity pressure. The unregularized models tends to have the most unstable validation loss after 10 to 12 epochs. Let's see the training based validation curves across all the models. So here we can see that without no regularization, training accuracy climbs high, but validation diverges after 12th epoch. Whereas for L1 regularization, both train and validation accuracy improve steadily but slowly. And for L2 regularization, smooth training and good generalization. Therefore, it's kind of good thing. So this confirms that the regularization improves the generalization, especially L2 for our case. That's it. Next, moving on to comparing CNN models with with and without dropout. So we will be using fashion MNIST dataset. So does dropout actually improve performance in CNN? That we are going to find out. So we'll be comparing two CNN models, one with dropout and one without dropout. We'll train both on the fashion MNIST dataset and compare how they perform in terms of validation accuracy and loss. First, we have to import the required libraries and then have to load the dataset. And then we're gonna go with no drop rate. Therefore, drop rate is 0, and with the drop rate, we're gonna train with 0.5 for 20 epochs. So here you can see that validation for validation accuracy for no dropout and dropout. The dropout model improves more steadily over time and avoids sharp fluctuations, whereas the non-dropout model reaches slightly higher accuracy in early epochs but starts showing signs of overfitting around 10 to 12th epoch. So this confirms that dropout slows training slightly but helps maintain stable performance. Then moving on to comparing the validation losses. So the dropout model maintains lower loss values and avoids sharp spikes, whereas the model with a dropout dips early but gradually creeps up. This kind of classic overfitting behavior. So here basically loss tells us how well calibrated the predictions are, even when accuracy appears similar. And then moving on to various accuracy and dropouts with and without dropout, we can see that here accuracy without dropout, the training accuracy keeps climbing, whereas the validation accuracy stagnates, and there is a clear gap indicating there is overfitting. And accuracy with dropout. Here training accuracy is slower because neurons are basically dropped, whereas the validation accuracy matches the training more closely. And here the smaller gap indicates better generalization. And if we see the loss training loss and high validation loss, it's not a kind of good. And loss without dropout, we can see that there is higher training loss as expected, but validation loss stays low and stable. So here we can see that dropout reduces overfitting by preventing co-adaptation between neurons. It forces the model to learn redundant, robust representations. That's it about this with and without dropout comparison of CNN models. Next, moving on to early stopping the CNN model. So here as well, we'll be using Fashion MNIST dataset. So here we're gonna train the model for 30 epochs, one versus one that uses early stopping with a patience of 3 to save time and to prevent overfitting and get better generalization with fewer training steps. Early stopping is suggested. First, we have to import the required libraries and then have to load the dataset, training and testing splits respectively. So first model fixed is trained for 30 blocks with no callbacks. So we use batch size of 64. Uh, so and verbose equal to 2 to view training loss. Basically, these acts as our baseline. And then now, after training it for the 30 epochs, we define a callback for early stopping. So this means if validation doesn't improve for 3 consecutive epochs, stop training and revert to the best weights. We train the model early with the same architecture and batches, but using the feature of callback. So as expected, it stops early, often saving time and avoids overfitting. And let's see the validation accuracy and the loss. We can see that early stopping stops around 12 to 15 epochs, whereas the fixed model reaches a similar peak but often declines in later epochs. If you see the validation loss, early stopping curve levels off gracefully, whereas the fixed model starts raising after epoch 15th, clearly indicating it's kind of overfitting. So this highlights that why we always don't need 30 epochs for training. And then accuracy for no early stopping, we can see that the training accuracy keeps climbing, and whereas the validation plateaus or even kind of dips. And the accuracy with the early stopping, in this case, we can see that both training and validation curves are smoother, therefore smaller gap indicating better generalization. And here, loss in case of no early stopping, we can see that the training loss drops steadily, validation loss increases midway. It's not a kind of good sign. Whereas loss with early stopping, it's controlled minimal, and we can see the divergence between train and validation loss. So the model stopped just in time before it started overfitting. So, so the validation accuracy without no early stopping is that when we run 30 box is around 91.6%, whereas with early stopping is 90%. So it's kind of close. So we can see that over 50% training time with almost same accuracy. Thank you. Next, moving on to Monte Carlo dropout. So traditionally, deep learning models give one prediction, but they never tell you how confident they are. That's a problem in real world applications like healthcare or self driving cars, where knowing what the model doesn't know can be crucial. So here as well, we are going to use MNIST dataset and enable draw operate at a inference time and perform 30 forward phases, all to estimate predictive variance and confidence. So just import the required libraries, configure the train and test split of the dataset, load it, and then here the dropout layer remains active at inference time by setting training equal to 2 during prediction later. So basically this simulates sampling from distribution of models, each with different dropout masks. So we compile the model using Adam optimizer and sparse categorical cross entropy. And then Now comes the Monte Carlo trick. So we select 100 samples from the validation set, and then using training equal to true, we perform 30 forward phases each time with a different dropout mask. So this gives us 30 different predictions for each of the 100 images, and the result is kind of stored in the tensor 30, 100, 10. Therefore, 30 predictions for each of 100 samples over 10 classes. So this captures the variability introduced by the dropout, which we interpret as uncertainty. So here we can see that the mean prediction across 30 runs, this is kind of our best case, and the standard deviation, this is our uncertainty per class. These are the various values. The prediction confidence and the uncertainty for the various images and samples. So here the deterministic accuracy, when training equal to false, therefore a single forward pass without dropout, the accuracy around 88%, whereas with the MC dropout, mean prediction, using 30 predictions with training equal to true, its average is around 90%. Therefore, Monte Carlo averaging smooths out the randomness introduced by the dropout and gives better calibrated results. That's it. Thank you.